the density perturbations of the 3/4. This logic also can, if you imagine that we have dark matter and dark matter WIMPs, it also explains another interesting numerological sort of coincidence that many people have remarked on, which is this, which is the mystery of the equidistant scales. That the weak scale appears to be the geometric mean of the scale associated with the cosmological constant and the Planck scale. The reason for this is that if we have dark matter as a thermal relic, by the usual Friesel calculation, again, going back to Weinberg, we can estimate what the temperature at matter radiation equality is given simply by 1 over the annihilation cross section for dark matter in Planck units. And so that's something like m dark matter squared over some alpha squared associated with the annihilation, some weak coupling factors alpha squared m Planck. So Weinberg tells us that we have to have the scale of the cosmological constant set by matter radiation. Matter radiation is given by this formula, so it's roughly m dark matter squared over m Planck. And if we imagine that dark matter is given by WIMPs, particles actually near the weak scale, then we would get, we would understand why the scale of the cosmological constant is related to the weak scale and the Planck scale in this geometric mean way. Now, there is some theoretical support to this picture, which, of course, famously, people polemically debated a great deal in the early 2000s. One is that string theory is a prime example of what a unique underlying theory could look like, but which has an enormous landscape of, let's call it 10 to the thousands of metastable non-supersymmetric vacuum. And just to sort of push the point and decouple it from the complications of string theory, there's a toy model for what's going on. Imagine the Lagrangian, the world is unique, but really unique, but it's the standard model plus n scalar fields and n decoupled scalar fields. Each one of them has a potential that looks like this, but all the potentials are a little bit different. So the Lagrangian is unique. We have, let's say, 1,000 scalars. It's not so many. We already have 100 degrees of freedom in the standard model. But the point is that even though the Lagrangian is unique, we'll have 2 to the n different possible values of the energy, depending on which minimum the scalar finds itself in for each one of these different guys. And so simply statistically, there's going to be one of them within 2 to the minus n, the ultraviolet scale of the theory of the origin. Okay, so that's an example of how we can get, even with a unique theory, a huge number of different an exponentially large number of different possible metastable vacua, enough to sort of finally scan all the many different possible values of the cosmological constant. And the second piece of theoretical support is from cosmology that eternal inflation gives a plausible mechanism for populating the landscape. Now, of course, it's suspicious that we would be invoking the presence of all these vacua out there beyond our cosmological horizon in order to explain something about what we see inside our cosmological horizon, and especially ironic that to try to explain the tiny size of our observed vacuum energy, we would be talking about things that are outside our cosmological horizon that are literally made impossible to see by that very acceleration whose tininess we're trying to explain by invoking them. But so that's suspicious, but on the other hand, it could be like that we're on the inside of a black hole. After all, being inside this accelerating universe is a little bit like being on the inside of a black hole. And so could it be the things that we naively think are there outside the black hole are encoded in some scrambled way in physics that we can in principle access inside? So that's something like that is expected to be the case to resolve the black hole information paradox. So maybe there's maybe something like that would make sense in cosmology as well. Let's just say that it's not obvious either way whether this is garbage or not to talk about all these vacua outside in order to try to explain something inside. I also want to stress, though, that there's an aspect of this physics that is not metaphysics. If we go back to this toy example of n scalars, imagine that was the actual model. Those scalars can, in principle, be seen by experiments in our universe. So you could, in principle, with a high enough energy accelerator, make all these scalars, confirm that the potential looks like this. You could even build bubbles of the other vacua, small bubbles of the other vacua, in principle, verify the couplings vary by shooting things into these bubbles and seeing them come out. So this part is not metaphysics. It's in principle possible from measurements in one universe to conclude that your theory is such that it gives you an exponentially large number of metastable vacua. And if we saw something like that, it would clearly change our thinking about naturalness problems. The part that we don't know how to make sense of is the sense in which these states are or aren't out there somewhere beyond our cosmological group. All right. Now, but we're unlikely to do this anytime soon, obviously, have big enough accelerators that could see all of these different, to produce all these other states and make these bubbles of the other vacuum and so on. So I think what we can do is think if this way of thinking could impact any other aspect of our thoughts about high energy physics. And there's the obvious question going back, and the obvious suggestion going back to very nice arguments of Donahue and others. Could there be anthropic explanations for the Higgs mass? And there's a very natural one, that if we, again, leave everything the same and we make the Higgs mass squared more natural by making it more negative, let's say, then if the Higgs wave just gets 3 times bigger than the observed value, then we don't have atoms, plural, anymore, because the neutron-proton binding energy, the down quark, gets so much heavier than the up quark that the mass splitting between the neutron and the proton exceeds nuclear binding energies. And so we don't have anything other than hydrogen. Okay, so if we make the Higgs wave much bigger, just by a factor of 3, the long distance world changes in a dramatic way. We don't have all this interesting chemistry. That's an accident of where the Higgs is. This is not remotely as compelling as Weinberg's argument, but it's still rather striking. In the opposite direction, if you make the Higgs mass squared more positive, then QCD breaks electroweak symmetry, and you can show that that all baryons are wiped out by scaleron processes in a world like that. So there is something interesting that if we take the standard model and we imagine making the 2 parameters that are fine-tuned, if we make the cosmological constant a little bigger and the Higgs mass squared a little bigger, it's striking that the world changes dramatically, that it's either empty in the cosmological constant side or no atoms on the Higgs mass squared side. And this is striking. It didn't have to be. And it's a true fact. It's a true fact that would just be a curious fact in the unique vacuum worldview, but you could take it as evidence that somehow the existence of a landscape could actually impact not just our understanding of the cosmological constant, but also of the hierarchy problem and the origin of the Higgs mass. And this is, after all, the sort of central tension of beyond the standard model physics has been between arguments that say that naturalness for the Higgs is correct. We have the picture of supersymmetry, the beautiful unification of coupling constants, dark matter that just fall in our laps on the one side, versus indications for unnaturalness on the other side, that there's no such argument for the cosmological constant. From the very beginning, we didn't have evidence for plate-between neutral currents, electric dipole moments, and so on that should have been there if we had natural solutions to the hierarchy problem. And then, of course, over the past decade, where the hell is everybody? Where are all the particles that are supposed to be there in the usual natural worldview associated with the Higgs? And for me, Weinberg's argument extended to possibly thinking about an anthropic origin of the Higgs, made it possible to entertain this possibility, which is at least my own picture. If someone woke me up in the middle of the night, put a gun to my head and said what I think is going on, I think what's going on is some version of minimal split SUSY, which is a very particular realization of supersymmetry, which is very unusual from the standard point of view, where the scalars are a parametric loop factor 100 or 1,000 times heavier than the fermions. In this picture, we still retain the successes of supersymmetric unification, dark matter. We get rid of all the phenomenological problems associated with the flavor-chain neutral currents and so on. The bottom of the spectrum should be near the TeV scale to be dark matter, but that could mean, in the simplest picture for dark matter, something between 1 to 3 TeV, which would be very easy to miss at the LHC, but would be accessible to a 100 TeV collider. This picture did correctly predict that the Higgs mass should lie in this range between 120 GeV and 135 GeV. It's a very mild prediction, but at least it wasn't wrong. And what I want to stress, though, is that this is a picture of the world which we could imagine getting evidence for from experiments, which would be completely crazy without the landscape, but would be quite plausible with it. All right, so that's all I wanted to say. I just wanted to end by saying that I was going to put that Weinberg was my hero and ideal in theoretical physics, but he really continues to be my hero and ideal in theoretical physics. And he somehow struck the perfect balance, as Riccardo also said in the very first talk, between direct contact with experiment and phenomenology on the one hand, but strong tie to formalism, but not just formalism for doodling around's sake, but formalism with a deep physical point on the other. And he managed to combine this style to be right about the real world, the actual world when we look at, when we see outside our window over and over again. And I hope, and I'm sure that his example will serve as an inspiration for us for decades to come. Thank you.
Thank you very much, Nima. And